Okay, so now that we have discussed the need for a probability theory that is based on some basic intuitive ideas of what we consider to be true in reality, we can describe what is a good theory of total probability and of probability, and this has become the modern interpretation of probability theory. Our modeling problem is that we want to reason in quantitative terms about the likelihood of events that we can observe, and these values have to be independent of interpretations by different people. So all reasonable people must come with the same results. So what we require is we need to be able to describe all the events in which we're interested in our experiment. We must be able to combine all these events into different sets or groups of events, and such as, for example, talking about not just individual packets arriving in a system, but all packets arriving within 5 seconds of latency, or not just about each individual customer arriving at a bank, but all the customers arriving at the bank during the first couple of hours of opening time. And we need to assign a number to each of these events that reflects the likelihood that the events occur in a way that is objective and yet is intuitive. Okay, now so we can start defining our probability theory based on this need to be objective and yet intuitive. And we think of the probability of an event as a number that we assign to the event that reflects the likelihood with which the event takes place. And the probability law is a rule that assigns these probabilities, i.e. these numbers, to events in a way that follows the intuition that any reasonable person would have regarding how reality works. So we need a formal way to assign these numbers to events. We need to be able to combine events arbitrarily and assign these probabilities, these numbers, in a way that it always agrees with the intuition we have about the reality that we experience and the intuition we have with which events occur in reality. To have a more formal description of probability, let's define capital E to be a random experiment. We will use capital letters to denote events. So A is an event in our experiment, and the probability of an event A we will denote as P of A. And a probability law for our random experiment is a rule that assigns these numbers P of A to each event A in a way that the following 3 conditions are satisfied. And these 3 conditions are taken from our daily experience and are the only 3 conditions that we require to be intuitive, which means we assume without proof. And those 3 conditions are that an event A, in this case, may or may not take place, and it has some likelihood of taking place. And that likelihood we define to be 0 if it never occurs. This definition of 0 for things that are or events that are impossible is for convenience. We could have chosen 1,000, 15.5, or some other strange number, but it makes much more sense to use 0 as the probability that something doesn't ever occur for convenience. Another intuitive concept is that something has to take place in our experiment. And then last but not least, intuitively we believe that if one event negates another, then the likelihood that one or the other event takes place is simply the sum of their likelihoods. And this is a direct consequence of our basic notion of counting. When we have two discrete elements, it's intuitive to believe that we have one element or we have the other element, and if one negates the other, then we can only have one or the other. And if we assign these probability values to that leads to the intuitive notion of exclusive events. So with these three intuitive beliefs, we have to build all of our probability theory. Describe in a bit more detail how we describe a random experiment, and we specify our experiment by stating an experimental procedure that we use and a set of measurements and observations. So we assume that our procedure doesn't introduce any randomness or errors. Any randomness that we observe is a direct result of the underlying randomness in the experiment, not our measurements. Examples are counting the number of packets that are received correctly at an access point in our Wi-Fi deployment. We count how many transmissions are required for a message to be decoded correctly at the receiver when we send the message through a noisy channel. Or we count the number of users accessing a server over a period of time. This procedure that we use doesn't introduce any randomness. All the randomness is inherent in the underlying experiment itself. We denote the set of possible outcomes in our experiment by omega or capital S, and we call that the sample space. And any set of elements can be a sample space. The only thing that we require is that performing a random experiment must result in one outcome. We cannot have our experiment not resulting in something. And we are going to denote this set of all possible outcomes by capital S or omega, depending on the setting. Examples of sample spaces are the following. If we have the experiment consisting of tossing a coin once, the possible outcomes can be we experience a head or a tail, so we have two outcomes, and our sample space omega has those two outcomes. If we toss our coin twice, then we can have two heads, head tails, tail heads, or two tails, and so we have four possible outcomes. If we have the experiment consisting of tossing two dice, then our sample space omega is this set of tuples with the value of each of the two dice. So we have from 1, 1 all the way to 6, 6, so we have 36 tuples. If we have the experiment consisting of measuring time in the interval from 0 to t when a failure occurs, then the failure may take place at any point in time between 0 and t, and any interval has an infinite number of instants, so our sample space is infinite. So we can have sample spaces that are finite, as in the first three examples, or sample spaces that are infinite. And our probability theory must account for finite or infinite sample spaces. We also have to define very clearly what we mean by events, and any event associated with a random experiment corresponds to a proposition. And remember that a proposition in mathematical terms is a statement that can be only true or false, but not both. And then, if that being the case, by using the mathematical notion of proposition, or the logical concept of proposition, an event takes place if any of the outcomes in the event takes place, which means that the proposition that with which we define the event becomes true. So any event is associated with a subset of the sample space omega as a result, and of course can be an empty set. An impossible event corresponds to the empty set phi. Examples of events: if we have the experiment consisting of tossing a coin twice, so omega goes from 2 heads to 2 tails, the event consisting of observing one tail has 2 outcomes, head tails and tail heads. The event of observing some tails can consist of the outcomes head tails, tail heads, and 2 tails. And the event consisting of no tails or heads is the empty set. It's impossible because something has to happen in our random experiment. We have to have one of these 4 outcomes. If we have continuing with examples of sample space and events, if the experiment consists of measuring the lifetime of a light bulb, any non-negative real number can be considered as the lifetime of our light bulb in hours, for example. So the sample space is the set of real numbers that are non-negative, and an event in that omega can be the event that the light bulb lasts at least 100 hours, and that we would represent by the set of values such that the value is larger than or equal to 100. The event if the light bulb lasts at most 1000 hours, we can express as the set of values x such that x is at most 1000. And the event g that the light bulb lasts exactly 1.5 hours is the set of values x such that x is equal to 1.5. So you see that we inherently require the use of the notion of sets. So going back to our definition of probability theory, is a mathematical model that we use to quantify the likelihood of events that take place in an experiment in which events are random. And it consists of our sample space that we denote by omega or capital S, and that sample space is the set of all possible outcomes in our random experiment. It has a set of events that we denote with F, and is the set of all subsets of the sample space. You may recall from discrete mathematics or other courses that we also call this as the power set of omega. And we have a probability measure defined according to our probability law, and we have a probability value for each and every one of the events in our sample space. So, as we stated, there are 3 conditions intuitive that correspond to our intuitive notion of what likelihood is in reality, and we have to develop our probability theory based on these 3 intuitive notions of likelihood. So a probability law for our random experiment E is a rule that assigns this probability number, P of A, to every event A in our random experiment, and such that it satisfies these 3 axioms that are also called Kolmogorov axioms. The first axiom is that the probability of an event A is non-negative. The probability that of the sample space itself is 1, and if 2 events negate each other, so the intersection of the 2 events is empty, or put it in another way, if no outcome that forms part of A can be part of another event B, then it is true that the probability with which either A or B takes place equals the probability of A plus the probability of B. We now can see why these three axioms are exactly the same as our three intuitive notions of likelihood. So the first axiom corresponds to our intuitive notion that an event A may or may not take place, and it has some likelihood. And for convenience, if it doesn't occur, we assign a 0 to that case. And once we have made this convenient assumption, then the intuitive notion that an event may or may not take place and it has some likelihood, then it follows that the probability of any event A has to be larger than or equal to 0. The intuitive notion that something must occur in our experiment results in the probability of something taking place being 1, because we are certain that some of the outcomes, one of the outcomes in our sample space will take place. So we are certain that we will observe one of the possibly many outcomes in our sample space. And the third axiom follows also from our intuitive notion that if one event negates another, then the likelihood with which we can witness one event or the other event equals the likelihood with the sum of their likelihoods. If it's easy to map this last axiom to our basic notion of counting. And this surprising small set of truths that are derived from our intuitive belief of how likelihood works in reality is all that we need to assume in probability theory, and that together with calculus and other mathematical tools will allow us to derive all the results in probability. And they were derived by Kolmogorov in the 1930s, and we will discuss later in the course that it took quite a while for this modern view of probability theory to evolve, starting from the Greeks or probably before them all the way to the 1900s. It took that long a time for people to have this clear view of what probability theory should be. So while now we can think is simple, it needs a lot of intuitive feeling, and that's part of what we're going to try to do, to try to think about this intuition behind the axioms and the intuition behind the corollaries and the more complex results. And to do that, we will rely on engineering examples to show that the results we derive are actually a natural consequence of these intuitive beliefs we have of likelihood. And if we follow formal logic, we can derive more and more complex intuitions based on these three basic notions of how reality works.